And today we are going to learn about the conditional variance. Okay, so this is the example 5-5. What is the conditional variance of y given x is equal to 1? And for the case of the joint probability mass function, the conditional variance was Vy given x is equal to the summation of y minus mu, the conditional mean, mu y given x square by the conditional probability mass function of y given x, right? Do you remember this equation? So, to solve this, the conditional variance of y given x when x is equal to 1 is the conditional variance of y given 1, right? And this should be equal to the sigma y is from 1, right? 1 to 4. Y is from 1 to 4, and y minus the conditional mean square by the conditional probability mass function of y given x when x is equal to 1 and y. Okay? We have to solve this equation here. And to calculate this equation, we have to know about the conditional probability mass function, right, of y given x. So, as we have already done, we calculated this conditional probability distribution table, right, to easily solve this problem. So, based on this table, we can solve this equation. That is the 1 minus, what is the conditional mean? There was 3.55. Okay? In the previous class, we already calculated this mean. So that is 3.55 square by, what is the conditional probability mass function of y given x when x is equal to 1 and y is equal to 1? That is 0.05 here, right? That is the conditional probability mass function. So 1 minus 3.55 square by 0, okay, plus 2 minus 3.55 square by, what is the conditional probability mass function of y when y is equal to 2 and x is equal to 1? That is 0.1 here, right? So that is 0.1 plus 3 minus 3.55 square by conditional probability of y when y is equal to 3 and x is equal to 1, that is 0.1 here, plus 4 minus 3.55 square by this value, right? This is the conditional probability mass function of y when y is equal to 4 and x is equal to 1. So that is 0.75. Okay? So based on this equation, we can obtain this equation. And if you solve this equation, the answer will be 0.748. Okay? So we can simply calculate the conditional variance of y given x when x is equal to 1. And now I'm going to explain about what is independence. And to understand the independence, we have to first know about the dependence, right? That is the reverse concept. the dependence implies that the values of x are influenced by the values of y, right? This is the case of the conditional problem, okay? So the random variable independence means that the probability of x does not change associated with the values of y. That is the definition of the independence. And in this case, the random variables x and y vary independently, okay? And this is the examples of the independence. In a plastic molding operation, each part is classified as to whether it conforms to color and length specifications. Define the random variables x and y as follows. X is equal to 1 when the part conforms to the color specifications, and x is equal to 1 otherwise. And y is equal to 1 when the part conforms to the length specifications, and y is equal to 0 otherwise. And we can assume that the joint probability distribution of x and y is defined by this equation, right? fxy, x comma y, can be shown in the following figure 5-4a. And this is the figure. And to express about the joint and marginal probability distributions of x and y. And these are the discrete random variables, x and y, okay? And these points indicate the joint probability mass functions, okay? And also, these two values and these two values indicate the marginal probability mass functions of y and x, okay? So based on this figure, we also can use this table, right? We have already learned. And these values indicate the joint, the result from the joint probability mass functions, okay? And these columns indicate the result from the marginal probability mass functions of y and x, right? So in the case of the independence, the joint probability mass function of x and y should be equal to the multiplication of the marginal probability mass functions of each random variable, okay? That is the requirement. And I'm going to verify this equation. And if we say x is equal to 1 and y is equal to 1, okay? In that case, we are going to calculate the joint probability mass function first. That is f x y 1, 1. Okay? And what is this? Based on this table, the joint probability distribution function of x and y when x is equal to 1 and y is equal to 1, that is 0.9702, right? So this can be simply calculated as 0.9702. And in this case, we are going to calculate the marginal probability mass function, f x, okay? And what is this? Based on this table, the marginal probability density mass function of x when x is equal to 1, that is 0.99, okay? So that is equal to 0.99, and the marginal probability mass function of y when y is equal to 1, that is 0.98 here, okay? So the multiplication of the marginal probability mass function of x and y will be 0.99 by 0.98. That is equal to 0.9702. Okay? And as you can see here, the joint probability mass function And also, the multiplication of each marginal probability mass function is identical. Okay? And if you do the same calculation for the case of x is equal to 1, y is equal to 0, and x is equal to 0, and y is equal to 1, and x is equal to 0, and y is equal to 0, you're going to have the identical result, which means that the joint probability mass function is equal to the multiplication of the marginal probability mass function of each random variable. Okay? So, in the case of the independence, this relationship is always satisfied. Okay? And the conditional probability mass function of Fy given x is shown in the following figure 5-4b here. And these axes indicate the discrete random variables x and y, and these dots indicate the conditional probability distribution of y given x is equal to small x. Okay? And this is identical to, and this figure is identical to this table. Okay? And these values indicate the conditional probability mass function. And in this case, the conditional probability mass function of y given x should be equal to the marginal probability mass function of y. Okay? So in the case of the independence, this relationship is also should be satisfied, which means that regardless of the values of x, the conditional probability is equal to the marginal probability in the case of the independence. So I'm going to calculate this equation also. If we say x is equal to 1 and y is equal to 1, the conditional probability of y given x that is equal to the conditional probability of y given 1, right? And 1. Because we assume that x is equal to 1 and y is equal to 1, okay? So what is this value? Based on this table, the conditional probability of y when y is equal to 1, given that x is equal to 1, that is 0.98. Okay? So that is equal to 0.98. And what about the marginal probability mass function of y when y is equal to 1? Based on this table, the marginal probability mass function of y when y is equal to 1, that is 0.98. Okay? So that is also 0.98. And as you can see, these two values are identical. And also, if we calculate the same equation for the case of x is equal to 1 and y is equal to 0, and x is equal to 0, y is equal to 1, and x is equal to 0, and y is equal to 0, you can find out that these two values are identical. Okay? So, in the case of the independence, the conditional probability mass function is equal to the marginal probability mass function. Yeah, that's the requirement. So this implies that whether or not the part meets color specifications does not change the probability of the length specifications. So this is the examples of the independence. And so we are going to learn about the properties of the independence here. For random variables x and y, if any one of the following properties is true, the others are also true, then x and y are considered to be independent. The first one is that the joint probability mass function is equal to the multiplication of the marginal probability mass function of each random variable, okay, for all x and y. The conditional probability of y given small x is equal to for x and y with the marginal probability as function of than 0. And also, the conditional probability of x given y is equal to the marginal probability mass function of x, okay, for all x and y with the marginal probability mass function of y is larger than 0. And lastly, the probability of when x is included in a set A and y when y is included in a set B is equal to the multiplication of each probability. This is the identical concept with the number 1. Okay? So this should be satisfied for any set A and B. Okay? So in the case of the independence, these 4 properties should be satisfied. Okay? And now I'm going to explain about the multiple discrete random variables. And up to this page, we have learned about the probabilities by using only 2 discrete random variables, right? X and Y. But in some cases, more than 2 random variables are defined in a random experience, and the concept presented earlier for the case of 2 discrete random variables can be easily extended, okay? And you guys can see how we can extend the equations from now on. And the notation of the discrete random variables simply can be adopted using the subscripts as follows. For example, x1, x2, x3, and blah, 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 xp, okay? So the numbers of the discrete random variables can be expressed by this simple subscript from 1 to p. Okay? We are not going to use x and y anymore. Okay? And first, we have to know about what is multiple mass function, right? And the joint probability mass function of x1, x2, blah, 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 xp is expressed by the following equation. The joint probability mass function of x1, x2, blah, 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 xp is equal to the probability of x1 when x1 is equal to small x1, comma, right? x2 equals to small x2, comma, blah, 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 xp equal to small xp. In the case of 2 discrete random variables, the joint probability mass function was equal to right? Do you remember this equation? And in this case, just the number of random variable is increased. But the idea and the equation is identical. Okay? Okay? So this should be satisfied for all points from x1 to xp in the range of large x1 to large xp. And if x1, x2, blah, 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 xp are discrete random variable with the joint probability mass function here, the marginal probability mass function of any xi is equal to this equation. The marginal probability of xi is equal to the probability of xi when xi is equal to small xi. That is the summation of the joint probability mass function. Okay? And in the previous case, the marginal probability mass function of x was the summation of the joint probability mass function. Right? Do you remember that? For the y. Okay? So, this is the same formulation, but the number of random variable is increased. Okay? So, what about the mean and variance for the case of the multiple random variables? The mean and variance, which is called EXI and VXI for I, when I is equal to 1 to blah 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 p, can be determined from the joint probability distribution of x1, x2, and xp as follows. Okay? And in the case of the ordinary probability mass function, what was the mean? So Ex was the summation of x multiplied by probability mass function, right? In this case, just the number of, just the probability mass function is changed to the joint probability mass function, right? Because the number of random is not 1 anymore, okay? So, this can be easily extended from this basic equation, okay? And also, the variation is also can be expressed by this equation. Why? The variance of the ordinary or normal probability mass function was the summation of x minus mu squared by the probability mass function. Okay? So, this just changes to the variance xi is equal to the summation of xi minus the mean of xi squared by the joint probability mass function x1, x2, xp by x1, x2, xp. Okay? This is the same formulation, but also just the number of random variable is increased. So the probability mass function is changed to the conditional probability mass function. Okay? That is the only difference. So this is about the mean and variance for the case of the multiple random variables. The sum is over all points in the range of x1, x2, blah, 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 xp. And next concept is the conditional probability distribution. The conditional probability distribution can be developed for the multiple discrete random variables by the simple extension of the ideas used for the 2 discrete random variables or 1 discrete random variable. For example, the conditional probability mass function of x1, x2, x given x4, x5 is expressed by this equation. Okay? This is the conditional probability equation, right? The conditional probability of x1, x2, x3 given x4, x5 is equal to the joint probability mass function over the marginal probability mass function of x4 and x5. Okay? So in the case of two discrete random variable case, the conditional probability of y given x was the joint probability mass function, right, over the marginal probability mass function of x. Do you remember this equation? Okay? And as you can see, this is the same formulation, but the number of random variable is just increased. Okay? But in this case, since we use the marginal probability mass function of xn4 and xn5 used for the denominator, this should be larger than 0. Okay? And that is the requirement. And this is the last concept of the multiple discrete random variables for the case of the independence. Okay? The concept of independence can be extended to the multiple discrete random variables. And discrete random variables x1, x2, blah, 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 xp are independent if this equation is satisfied. What is this equation? That is, the joint probability mass function is equal to the multiplication of the marginal probability mass functions of each random variable. Okay? This is the same concept, but just the number is different. Number of random variable is different. For all x1, x2, blah, 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 xp. Okay? And so we can very simply understand about the multiple discrete random variables case. And now, we are going to learn about the multinomial distribution, which is called 다항분포. And to understand the multiple probability distribution, we first remind what is the binomial distribution. Okay? Binomial distribution is called 이항분포. Okay? And the binomial distribution has the following characteristics. The first one, it has a fixed number of trials. Okay? That is called n. And secondly, each trial is determined as success or failure. So that's why we call this is the binomial distribution, which is called 이항. Okay? We have only two options. And in this case, x is the number of success. Okay? So when the number of trials is fixed, we have to calculate the probability of the number of success. Okay? That's the concept of the binomial distribution. And the probability of success in each trial is constant. Okay? And the trials are independent. These are for typical characteristics of the previous binomial distribution. So for examples, we flip a coin 10 times and let x denote the number of heads obtained. And in this case, the number of trials is fixed as 10 times, right? And also, we have only two options. The first one is that we obtain heads or we obtain the tails. Okay? 앞뒷면. So, in this case, we only have two options and the number of trials is fixed. So, we can apply the binomial distribution concept. Okay? And secondly, on one motion tool produces 1% defective part, and let x denote the number of defective parts in the next 25 parts produced. And in this case, the number of trials is also fixed here, next 25 parts produced, and we have only two options that we can obtain the defective part or non-defective part. So this is also the concept of the binomial distribution. And lastly, for all bits transmitted throughout a digital transmission channel, 10% are received in error. Okay? Let x denote the number of bits in error in the next 5 bits transmitted. In here also, the number of trials is fixed as 5 bits. Okay? And we have two options that we can receive the bit in error or we can receive the bit without error. Okay? So this is also the concept of the binomial distribution. And please remember this concept, okay, of the binomial distribution. And I'm going to explain about the multinomial distribution. And we can suppose that a random experiment consists of a series of n trials, okay? And we can assume that the outcome of each trier can be classified into one of the k cases, okay? And the probability of a trier resulting in one of the k outcomes is constant, denoted as P1, P2, blah, 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 Pk, right? In this case, we have k cases, so each case has a different probability, okay? And the triers are independent, okay? In this case, the random variables x1, x2, blah, 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 xk, that denote the number of triers that result in case 1, case 2, case k respectively, have a multinomial distribution, and the joint probability mass function is given as this following equation. Okay? So the difference between the binomial and multinomial distribution is that in the case of the binomial distribution, we have only two options, right? But in this case, we have multiple options from 1 to k. Okay? And each case has different probability. So the joint probability mass function for the case of the multinomial distributions is equal to n factorial. This is the number of total triers, right? Over each trier, number of each trier, x1 factorial, x2 factorial, blah, 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 xk factorial, by, these are the each probability, right? And these are the each number of triers, okay? So P1 to x1th power by P2 to x2th power, x2 x second, blah, 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 Pk to xkth power. And in this case, the summation of the number of each trier should be the total number of triers n, right? And also, the summation of all probability should be equal to 1. Okay? So, how we can obtain this relationship can be easily understood based on the following example. And this example, okay? And of the 20 bits received, what is the probability that 14 are excellent, and 3 are good, and 2 are fair, and 1 is poor? In this case, we have total 4 options, right? So this is the type of multinomial distribution case. And we can assume that the classifications of the individual bits are in, and the probabilities of excellent, good, fair, poor are 0.6, 0.3, 0.08, and 0.02 respectively. And as you can see, each case has different probability, right? And one possible sequence of 20 bits that satisfy the above request is we can obtain the excellent, right? And excellent, blah, 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 excellent, and G, good, good, and fair, fair, and poor, right? This is one typical sequence of 20 bits that satisfied this requirement. And the number of excellent is 14, right? Because in the example, 14s are excellent, and 3s are good. These are 3, and these are 2, and these are 1. And if we say this is the A, okay? And what is the probability of A? What is the probability of A? That is 0.6 to 14th power, right? By 0.3 to 3rd power, right? By 0.08 square by 0.02 to 1th power. and this is equal to 2.708 by 10 to minus 9th power. What is this? That is the probability 1 to x1's power, right? By probability 2 to x2's power, and probability 3 to x3's power, and probability 4 to x4's power. Okay? Okay? So, using the independence, we find that the probability of this sequence, as you can see here, this is the probability for the case of one possible sequence. Okay? And however, the number of different sequences with 14 excellent, 3 good, and 2 fairs, and 1 poor is a lot, right? So, based on the previous chapter 2 about the permutations, which is called sunyal, the number of sequences will be we can say the total number of trials is 20, right? Based on the permutation, the number of sequences will be 20 factorial over 14 factorial by 3 factorial by 2 factorial by 1 factorial, right? So, this will be 2,325,600. Okay? So, finally, the request probability should be the probability of 14 excellent, 3 good, 2 fairs, and 1 poor will be the multiplication of these 2 values, right? Okay? So that is 2,325,600 by 2.708 by 10 to minus 9th power. So that is equal to 0.0063. Okay? So, based on this example, now we understand why we have to use this kind of relationship, right? This is the number of sequences based on the permutation, and this is the probability for the typical one sequence, okay? So, in the case of the multinomial distribution, the probability can be obtained based on this equation. And this is the next example. And in the previous example, 5-9, let the random variable x1, x2, x3, and x4 denote the number of bits that are excellent, good, fair, and poor, respectively. And what is the probability that 12 bits are excellent, and 6 bits are good, and 2 are fair, and 0 are poor? And now this is very simple, right? The probability of 12 excellent and 6 are good and 2 are fair and 0 are good, right? Right? Okay? P? Oh, sorry. here, right? So this is the total number is 20, right? 20 factorial over 12 factorial by 6 factorial by 2 factorial by 0's factorial by 0.6 to 12th power, 0.3 to 6th power, 0.082 square by 0.02 to 0th power, okay? And if you calculate this, the answer is 0.0358. Okay? And now, we are going to learn about the multinomial mean and variance. Each trial in a multinomial random experiment can be regarded as either generating or not generating a result in the case I for each I when I is equal to 1 to blah 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 k. Okay? And because the random variable xi is the number of trials that result in case I, xi has a binomial distribution. Therefore, if x1, x2, blah 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 xk have a multiple distributions of xi is binomial with the following equations. And for example, what about the mean and variance for the case of binomial distribution? That was n by p, right? And the variance is n by p by 1 minus p, okay? So remember that. And in here, we are selecting one typical random variable xi among the multiple random variables, okay? We can say xi, and in this case, xi has two options, that generating the result or not generating the result. For example, in the previous example, we have 4 options: excellent, good, fair, and poor. And if we select only one excellent, excellent has 2 options that it can produce excellent or not. Okay? Okay? So each xi has only 2 options. Okay? So this is following the binomial concept. So we can use this same equation, which means that the mean of xi is equal to n by the probability of I. Okay? Also, the variance of xi is equal to n by pi by 1 minus pi. Okay? So even though the case of the multinomial distribution, we can use the identical formulation for the case of the random variance xi. Okay? So this is about the multinomial mean and variance. So we have learned about the discrete random variables case. And now we are going to study about the 2 continuous random variables. Okay? In the previous chapter, we have learned about only 1 continuous random variable. But in this case, we are going to learn about 2 continuous random variables. Okay? So first, we have to define the joint probability density function. Okay? Not the mass function. Because this is the continuous random variables case, we have to use the joint probability density function, okay? The joint probability density function for the continuous random variable x and y, denoted as fx, x, y, this is the identical formulation. satisfy the following properties. First one, the joint probability density function should be larger than or equal to 0, okay, for all x and y. And also, the integration, we are not going to use the summation anymore because this is the continuous case. The integration of the joint probability density function of x and y from minus infinite to infinite should be equal to 1, right? And thirdly, for any region R of two-dimensional space, the probability that x and y are included in the region R should be equal to the integration of the joint probability density function of x and y over the region R. And this can be explained by this figure, okay? And we can say this is the continuous random variable x, and this is the continuous random variable of y, and the y-axis indicates the joint probability density function. And this is the region R, okay, the shaded area. And what is the probability that both random variables x and y are included in the region R? That is, there should be this shaded area, right? So there should be the double integration of the joint probability density function of x and y over the region R, okay? So for the case of the joint probability density function, these three definitions should be satisfied. And this is an example. Let the random variable x note the time in milliseconds until a computer server connects to a machine. And let y denote the time until the server authorizes you as a valid user. And this is also in milliseconds. And x and y measure the time of weights from a common starting point, okay? And also, the y is always larger than x. And assume that the joint probability density function for x and y is as follows this equation. Fxy, x comma y is equal to 6 by 10 to minus 6 power by exponential minus 0.01x minus 0.02y when y is larger than x. Okay? And to prove that the integration of the joint probability density function is equal to 1 in this case. That is the first equation, first example. And we have to verify that the joint probability density function of x and y, dx dy minus infinite to infinite. The question is that we have to verify this equation, right? Okay? For this case. And for this case, the joint probability density function is expressed by this equation first. And we can have 6 by 10 to minus 6 power by exponential minus 0.001x minus 0.002y. Okay? And we have to provide a double integration here. Okay? And first, from the example, the y is always larger than x, which means that the first integration should be from x to infinite dy. Right? Right? Because y is always larger than x. That's the requirement. So the starting point of y should be from x to infinite. Okay? And what about the dx? In here, x is time. There is a minus time? No, right? So that should be from 0 to infinite. Okay? Okay? So we are going to solve this equation here. And we can say this is the large A. And we are going to solve the large A here. And we can extract 6 by 10 to minus 6 power by exponential minus 0.001x from the integration, right? Because this is include the dy. That is from x to infinite exponential minus 0.002y dy. Okay? And equal to 6 by 10 to minus 6th power by exponential minus 0.001x by minus 0.002 exponential minus 0.002y from x to infinite. Okay? Okay? And this can be written as 6 by 10 to minus 6th power over 0.002 by exponential minus 0.001x by, what about the minus exponential minus infinite? That is equal to 0. So minus 0 plus exponential minus 0.002x. Okay? And this is equal to 0.003, and this can be eliminated. So finally, we have 0.003 by exponential. We can add these two values in the case of the exponential, right? Because this is connected as the multiplication rule. Exponential minus 0.003x. So this is the large x. Okay? And so we solve a here, and then we have to solve the integration from 0 to infinite 0.003 by exponential minus 0.03 x dx. Right? Okay? And we can extract the 0.003 here, okay? So that is 0.003 by minus 0.003 exponential minus 0.003 x from 0 to infinite. Okay? And this can be eliminated, okay? Right? So we only have to calculate the minus exponential minus 0.03 x from 0 to infinite. The exponential minus infinite is equal to 0. Okay? So that is minus 0 plus, what about the exponential 0? Yeah, that is equal to 1. So finally, this is equal to 1, okay? So we verify the integration of the joint probability density function equal to 1, okay? In this case, and this is the second question. What is the integration of the joint probability density function of x and y when x is smaller than 1000 and y is smaller than 2000? That is the question. And here we have to calculate the probability of x when x is smaller than 1000 and y is smaller than 2000. Okay? And in the case of the continuous case, this is equal to this, right? Okay? Based on the previous chapter, we have learned, right? Since the width in the curve is 0, so this is equal to this, and this is equal to this. So we can simply change this equation to this, okay? And this should be the double integration, okay? And 6 by 10 to minus 6th power by exponential minus 0.001x minus 0.002y dy and dx. And this is from x to 2000, right? And this is from 0 to 1000, okay? This is the example. And here we can say this is also large A. And large A is equal to 6 by 10 minus 6th power by exponential minus 0.001x by integration from x to infinite exponential minus 0.002y dy. Okay? And that is equal to 6 by 6th power by exponential minus 0.001x by 0.002 exponential minus 0.002y from x to infinite. This is equal to 0.003 by exponential minus 0.003x. Okay? Oh, sorry. This is 2000, right? And this should be 2000. Sorry. So, this should be 6 by 10 to minus 6 power over 0.002. We extract the 0.002, okay, by exponential minus 0.001x by minus exponential minus 4, right? 0.002 by 2000 is 4, and plus exponential minus 0.002x, okay? And this is equal to 0.003, so that is equal to 0. minus exponential minus 4 by exponential minus 0.001x plus 0.003 by exponential minus 0.003x. Okay? Okay? And this is the answer for the A. So we have to calculate the integration from 0 to 1000 by 0.003 by minus e minus 4 by exponential minus 0.001x plus 0.003 by exponential minus 0.003x dx. Okay? And this can be minus 0.003 by exponential minus 4 by minus 0.001 exponential minus 0.001x from 0 to 10,000 plus 0.003 by minus 0.003 exponential minus 0.003 x from 0 to 10,000. Okay? Okay? And this will be minus 0.003 by exponential minus 4 by minus exponential minus 1 over 0.001 plus 1, right? Exponential 0 is 1 over 0.001 plus 0.003 by minus 0.003 exponential minus 3 plus 1 over 0.003. Okay? And if you calculate this based on this scientific calculator, okay, the answer is 0.915. Okay? And based on these calculations, we can draw the diagram. And if we say that this is the random variable x, okay, and this is the random variable y, for this case, what is the y is larger than x? If we assume that this is the y is equal to x, okay, they should be this area, right? Because y is always larger than x. And this is y is equal to x. So this shaded part is indicate this one. So for this case, the x is more than 1000 and y is smaller than 2000, okay? X is 1000, and y is smaller than 2000. The probability was this shaded area, right? Okay, among this part. So the probability is 0.915 is indicate that this yellow shaded area have 91.5% of the entire area. Okay? Okay? So this is end of today's class. See you on Friday.